Hello everyone. I would like to welcome you all out to this webinar. Now, what we want to do is we're excited to release our Automation Starter Kit. Over the past few months, I've talked to a lot of users out there that are very interested in automation, but they weren't quite sure how to dip their toes in the water and start their journey towards automating some of their designs and making those whole processes more efficiently. So a little while ago, I was talking to one of our customers, OP Tanks, and as I was talking to them, they pointed out that they wanted the same type of help. And so they were very gracious enough to give us a data set that we could share publicly. And we went ahead and we took that, we put a whole bunch of automation in there so that all of you now will have a sample or an example of how automation works. And then you can start to pattern some of your automation solutions based on these same techniques that are used in this data set. So the way I want to move forward with our presentation today is I first want to take a few minutes to talk about what is the starter kit so you understand who it's for, how it works, what you can expect to get out of it. Then I want to start talking about what's actually inside the starter kit so that you know what you're getting, know how you can make it work. Then I want to make sure you understand how to get started. Just go over the steps of how do you unzip all of the files and get them set up so that everything works properly. Then I want to go over some important concepts that if you understand these concepts, when you look through the code, it will make a whole lot more sense what's going on. You'll be able to understand all the different steps that are being taken. And then finally, at the end, we want to go ahead and do a quick demonstration so that you guys can see how exactly the automation works. So the main purpose behind building this automation starter kit was to give a practical example of how to architect an design process. Now, in this specific case, we used a tank model that, again, was provided by OP Tanks. But in reality, these same concepts can be on any type of product that you design. Whether you're in the door and window industry, you're in the industrial machinery type industry, the medical device industry, whatever your industry is, you can take these exact same concepts that are going to be presented today and you can put those into your own design to make everything work properly. Now, as I mentioned, we do have the sample data set that is included, and that includes all of the necessary files so that you can create an automated 3D model. It also has documentation that helps familiarize users with the content and the setup of the overall solution. Who we actually made this for, we're really looking for beginners here. If you're an advanced user and you've been in the Inventor API for years, there might be a thing or two you might glean from this, but really this is designed for those that have never really done any automation inside of Inventor and want to start learning where they start, want to dip their toes in that water and start creating their automation. Now, that being said, it also would be beneficial if you had some type of beginner experience with Visual Basic Programming. If not, it's probably something that you'll want to just maybe Google real quick and do some type of a beginner Visual Basic Programming course because I assume that you have at least a base knowledge. And it would definitely help make the code a lot more readable and understandable if you at least have an idea of how code works and how it's put together. I didn't intend for this to be a Visual Basic course. I just meant for it to be, once you have a basic understanding, how do you apply that to CAD? Specifically, how do you apply that to Inventor? I also want to talk about what's not included. As I mentioned, this is not a Visual Basic course, so there's no instruction on that. We stayed away from drawing automation for right now. That's an entirely different animal. We want to first focus and start on how you design and automate 3D models. It's a lot easier to learn, and so we're just going to stick with that. We don't get into external rules for iLogic. I built all of the rules internally to the models, so everything is self-contained. We did not go over how to build add-ins or plugins, which basically means that if you look across the top of the toolbar inside of Inventor, there's not going to be any special icons that run the different commands that we're creating or the different automation. You have to open up the model and execute the application from the form that will come up, which you'll see here in a few minutes. I also didn't go into using Visual Studio for building solutions. Again, everything is built inside of the iLogic editor right inside of Inventor. And I didn't go over debugging techniques or even really give any guidance on debugging to make an application really robust so that it doesn't fail and it gives users good feedback when it does. There's really a whole art to that. Right now, I'm just trying to help you guys get to where you can build a functional solution. And then as you get more and more experience, there's all kinds of resources out there that can help learning and help teach you about debugging techniques. Now, I do want to make it clear that this was built on Inventor 2020. And so you do need to have at least Inventor 2020 for this to work properly. If you don't have Inventor 2020, then you can just download it and you can install it side by side with 2019, 2018, whatever version you're currently using. We have tons of versions of Inventor on our same machine here at KETIV. We do that all the time because we work on different projects and different versions. So you won't have a problem installing Inventor side by side. But as I mentioned, for the models to work, for the automation to work, you definitely do need to open this up inside of Inventor 2020 or 2021 will work as well. So let's go ahead and review the main parts of the tank. So first of all, we have the overall assembly, and that's where the high level logic exists that brings together the tank body, the skid assembly, the manways, the inlets, the outlets. All of that come into the overall tank assembly. Now, when you look through this is the main rule, and you'll learn how do I create iLogic forms. In there, there's a bunch of information that I embedded inside of an Excel file. And so you'll learn how to read data from Excel and just a bunch of tools of managing overall assembly creation. How do I put the right files in the right folders? How do I change references so that instead of referencing some template components inside of the assembly, it now references the new components that we copied over that we can change and modify. There's a lot of that type of logic built into the overall tank assembly. We next move to the tank body assembly, which is the main part of the tank here. What's nice about that is we do use an I part in this solution. This dish head right here is an I part. It's the only one that we used. The code is very simple because we just, based on the size that they select, we change it so that it comes in at the right size and location. But it does show you at least a little bit of how you can work with some I parts if that's a workflow that you prefer. We also show how to create assemblies with constraints. So to place all of these different shell plates, I actually use constraints rather than just placing them. And then we also show how to suppress some assembly level features. Now, I was going to go in and put a whole bunch of assembly level features. That's where we put the cuts for these different pipes that extrude through the tank. I only got a couple of them done just because I ran out of time. But based on the two that I did, this is a data set that you guys can experiment with. You guys can add on to it. So it might be a good exercise for you to learn how to go in and put in those other cuts that you would need and to learn how to put them in the right location and suppress them when you don't need them. Then we have the skid assembly, which is this green part right here on the bottom. This holds another sub-assembly called our saddle assemblies. And together that basically creates the whole support structure for the tank. So here inside of this saddle assembly, we have a couple, it's made of 3 sheet metal parts. Maybe you can see it a little better right here. There's a saddle piece here on the top and then a support plate that's vertical in the middle. And all of these get welded together. Based on the different types of skids that I might have to use, I have to sub that part in or out. So there's a good bit of code where you can see how we swap parts in and out based on a customer's need. We also show how to push parameters from a high-level assembly down to the component parts. In fact, that happens pretty much everywhere. So you'll have a lot of examples on how you can push parameters from upper-level assemblies down to its respective components, other sub-assemblies, and so forth. And then finally, we have the gunline assembly right here. And this one, I use the select case command to build in these nozzle assemblies that you see right here. So select case is a good way if you have multiple options in code, you can clearly delineate what needs to happen for each different option. And again, just like in the skid assembly, I sub library components into the assemblies as needed. So there's a lot of code that you can see how that works. Now, the rest of these, except for the sump, are pretty much just parts that we bring in as needed. Here's the manway, here's the drains, There's also a drain here in the front. This is the sump assembly, which I'll talk about in a minute. This is the inlet. And I do want to point out the inlets. The way I built this automation, you can insert it on the top or you can insert it on the front plate here that's out of sight. And for the sump, I used some trig to calculate how long this angled tube has to be here. So if you want to see how you can do some trig related functions, there's a rule inside of the actual pipe part that shows how to do that. This is also the only area where I use the try catch in Visual Basic. That's a way that you can have it try something if you're not sure it's going to succeed or if it's going to fail. And if it fails, then you can catch the error and do something with it, or you can just keep going if you don't care that it fails, basically. It's something that's used a lot when you want to debug an application or you want to make it much more robust so that it won't fail. But again, I didn't use it extensively. I just used it once, and at least there's an example where you can kind of see how that works. And then the pipe assembly for the sump, it combines a library component with some project-specific components. So you can see how you make references to library components and other parts that you need in and out and make changes to those as necessary. So there's a lot that you can really glean from this data set. I tried to put different pieces in there so that you could get a wide view of how automation is created. And then hopefully this will inspire you to architect the solution in a way that makes sense, that will help you guys start to have more efficient design processes. Now, the last thing I want to talk about with what's inside of the kit is the documentation. So when you unzip the file, you'll notice that 4 folders will come in, and workspace, that's where we have our main file. I just called it create-new-tank.iam, so it's really easy to find and double click and start. Then we have the template components. These are components that I'm going to copy into our new projects and we're going to change. So template components are components that are meant to be unique and are meant to change from one project to another. And then the library components, these are components or parts or assemblies that are meant never to change. Like the manways, that's just a library part. We're not going to make a different manway for each project. So, flanges are another example. So I have a whole bunch of parts in my library that I'm just going to pull in on an as-needed basis. I'm not going to make a new copy of them. There's no reason to do that. I'm just going to reference the parts that are already inside of my library. But now we get to this documentation folder, and in here I have code for project in PDF format. That's if you want to view it, you want to put it on one screen, and then if you're the kind that likes to type the code in so that you can learn it better and you can see how it all works together, that's good if you want to do that. I also have a whole bunch of copies in Word format so that if you want to copy and then paste it into the editor, you can do that with the Word document. And then I also have this iLogic user snippet for the Automation Starter Kit. So inside of iLogic, there's snippets, and there's some system snippets that you can't change. Those are the ones that are part of the iLogic package. But then there are custom user snippets that you can add. And if you go ahead and use mine, it'll actually put snippets for every bit of code that's used in this application. So you can literally just drag and drop it into your rule, and it will put everything there very quickly. So regardless of how you want to go through and try it and see how everything works together, there are multiple ways that you can rebuild it. Inside of the PowerPoint overviews folder, I have a copy of this presentation and a bunch of other presentations that give some more detailed information on each of the different parts of the tank so that you can get to know it a little bit better. And then finally, we have a list of parameters for automation Excel spreadsheet. And this is just so that there's a lot of parameters I use that represent different widths, the length of the tank, the OD of the tank, the height of the saddles. There's all kinds of parameters that I use, probably 70 or 80 in all. And so this is just listing those parameters out so that you understand what each one represents, which will hopefully make it a lot more sense as you're going through the code and you're seeing how all these different parameters interact to get us the final tank that we're looking for. So now I want to talk about how do we get started. So the first thing you need to do is download the kit. And you can see the URL right there, the ketiv.com/automation do-it-yourself kit. So if you go to that website, you can go ahead and register, and then that will go ahead and that will send you all of the information that you need so that you can download the kit, and then you can start to unzip it, which takes us to step 2. So in step 2, we basically want to unzip all the files. I recommend that you create a new folder on the C drive and you name it Automation Starter Kit, exactly capitalized, spaces between the words like you see here on the screen. The reason for that is that if you can get it set up exactly like you see right here, C drive, Automation Starter Kit, then these folders right in that Automation Starter Kit folder, everything is going to work out of the box and you're not going to need to do anything else. If you can't get your overall unzip files to look like this structure, there's a couple of additional steps that you're going to need to take at the end, and I'll get to that when we get to step 5 here in just a couple of minutes. Once you have everything unzipped, then you just need to open up Inventor, click Projects in the ribbon. In the project window, click the Browse button right here, navigate to where you unzip the files. You'll see a project file called Automation Starter Kit. Go ahead and click Open on that. And then once you have the project file set, make sure that that project is active. And then when you click Open in the Inventor interface, just make sure that you're in the workspace directory, which by default, it should bring you into that workspace or into that folder. And then double click the Create New Tank.iam file, and now you're inside the automation. Now to be clear, when you open up the Create New Tank IAM file, it's going to be blank. There's not going to be anything in the file, but then a form is going to pop up similar to the one that you see right here. What will basically happen is once you go through and you pick all the different options you want for your tank and you click this Create New Tank button, that's when it's going to go through and it's going to start actually generating geometry, and you're going to start seeing the tank build itself right in front of your eyes. And that's all of the code doing the work of bringing in the right parts, making the right changes, and building up your tank from the ground up. Now, as I mentioned, if you don't get your folder structure exactly the same way that I recommended it, maybe you have to put it on the D drive, maybe there's just somewhere else you wanted to put it, then a couple of extra steps you're going to want to do is before you hit that Create New Tank command, open up the parameters dialog, and in there's 3 paths that you'll need to update: the project path, the library path, and the template path. Just go ahead and change these values to match wherever those paths are on your machine, and very importantly, remember to put that / at the end. Without that / at the end, it won't work right, and you'll have the automation will come back and say, we can't find this file. So make sure that you put it just like this. The other part that you need to go in and change, there's a rule called Create New Tank. It's basically the main rule in that assembly file. You right click it and say Edit Rule. When you go in there, you go down till you find a subroutine called Get Parameters from Excel. When you find that rule, there's 3 different places where I have it hard-coded where to find the Excel file where it's going to pull information that we need for the configuration. And so you need to go to each of those 3 places and update them so that they reflect wherever the path is that SK Excel file is located. So as long as you make those changes and update those and make sure all the paths are correct, then when you hit Create New Tank, everything should work. If you have any problems, go ahead and email me and let me know, and we'll help get you fixed so that you can see it work and you can start going in and playing with the code. So now that you're set up, I want to go over some important concepts that as you go through the tank, you're going to need to understand. I want to first talk about a typical new design workflow. When I have to create a new tank in this example, but the product could be whatever you guys design where you work. What are the steps I have to go through to get a new version of that I can change and modify without affecting anything that has been created previously? Then I want to talk about different ways that we can place components inside of assemblies that are important to know and understand. I want to talk about passing parameters between files, and then finally building code inside of sub-assemblies. So first, let's look at the typical new design process. So let's say I have a new tank that I want to build. I might have a library of hundreds of tanks I've designed in the past. So I might go through and say, you know what? I remember another job I did that was very similar to this tank. And I might open that and save it and then start making changes to something that's already created rather than build it from the ground up. If I were going to do that, the steps I would take, in this case, let's suppose we have assembly A. We have a couple of parts, a sub-assembly inside of assembly A, and then maybe we have a couple of library files that we have that we're referencing so that we can build assembly A. Now, the first thing, as I said, I want to do is I want to make a copy of it. And notice that as soon as I make a copy of it, assembly C does not have its own unique version of part AA, part AB, or assembly AA. It just references the exact same files that assembly A was referencing. So if I make changes in assembly C to part AA, it's also going to affect assembly A as well. So understand that this is really the equivalent of going inside of Inventor and saying save as, and saving a file out, and then creating your new copy. Now, there are going to be some components more than likely that I'm going to want to change without affecting assembly A, which was my original assembly I copied from. So what I'm going to do is the parts that I do want to change, I'm going to go ahead and I'm going to make a new copy of those files that are fresh. And then I'm going to go in and I'm going to update the references so that assembly C, instead of referencing part AB and assembly AA, it's now going to reference its own copies of those files, which in this case I'm just calling part CB and assembly CA. Now, more than likely, the library files are going to stay the same. You know, in assembly C, you might want to change some of the library files it's referencing, but you get the point. Now, this workflow of changing the reference from part AB to part CB or assembly AA to assembly CA is really just a component replace inside of Inventor. So inside of Inventor, if you've ever had an assembly and you wanted to replace the reference of one file with another, chances are you've gone in, you said component replace, and that's exactly what we're doing here in this step. Now, why is this important? So first of all, for an automation solution, you want to have good file management. You know, I've seen solutions that have been created in the past that have not used good file management techniques, and they end up recopying the same file hundreds, if not even thousands of times. And so whenever you want to get your arms around that and start managing it better, no one has any clue which is the right part. It just creates chaos. I mean, yeah, it's good that you can do your design work fast, but you want to try to minimize duplicating parts and things like that as much as possible. So by doing this, you can have good file management techniques. As I mentioned, in code, I basically go through that same process that I just showed you over and over again, where I make a copy of the top level assembly, then I make copies of the components that I want to modify and change, then I update the reference so that my new assembly is referencing my new files rather than the old files. So this happens over and over again. A couple of commands that you'll see with me copying, I use Inventor assembly.saveas. You can see here's an example, this document.save as. And another one I use, so the Inventor assembly.saveas is just like going inside of Inventor with an assembly open and saying file save as. Another one I use is system.io.file.copy. This technique right here gives us access to Windows level functionality, like checking if files exist, creating folders, creating files, copying files. So this gives us a window into doing that. So really, when you look at this command right here, what I'm essentially doing is if I opened up Windows File Explorer, I right-clicked the file, I said copy, then I went to another folder and said paste. That's essentially what I'm doing with this line of code. I'm copying, making a copy of a file from one location to another directly. Now I want to go ahead and talk about placing components inside of assemblies. There's really two methods that we use in code. We use constraints, which most of you are probably familiar with because that's the typical workflow when you're building assemblies manually inside of Inventor. But we also use matrices or points to place parts where we want them specifically and orient them, and then we ground them so that they're exactly where we want them to be. So first let's talk about constraints. Like I said, most of you are probably familiar with this. That's where you take two surfaces of two different models and you say, mate these together, make them flush. You might pick a cylindrical surface of a bolt or a nut, and you might insert it into a corresponding hole inside of a flange or a plate or something else. So those are constraints. Now, there's an iLogic snippet for creating mates or constraints, not just mates. And it's right here. I mean, you can see there's a lot of information that you have to fill in. And so some of that looks a little bit intimidating, like you're not quite sure how to do that. There is an easier way to add mates with iLogic. You first bring up your assembly. You insert a component manually. You add your desired constraints just like you know how to do today. You say, I want a mate constraint, a flush constraint, and you build it up exactly the way you want it. Then you open up the iLogic editor. In the editor here, you can go to the Model tab, and if you right-click the part that you just added, there's a few capture current state options. You want to capture the one that includes the word constraints in it. And when you capture that, notice it gives you all of the code that you need to insert the part into your assembly and to constrain it. So then what you can do is you can save that rule and you can delete that component out of your assembly. And now if you run the rule again, it'll actually bring in that part and put it in the exact same place with the exact same constraints that you had before. So this is a very easy way. It's kind of like record macro in Excel. It makes it very easy to first manually do what you want to do, record the steps that Inventor went through to do that, and now you have the code that you need. Now the second way gets a little bit more involved, and so I want to take some time to really help you understand how we use points and matrices. It's a little bit intimidating, but with a little bit of guidance, it's actually really easy to learn, and it becomes a very powerful way when you're automating assemblies to put parts into your overall assembly, and it's really fast. It's a lot faster than constraints, and it takes a lot less computing time, and it's also more robust. You don't have to worry about surfaces somehow disappearing if geometry changes a certain way. You can always put parts exactly where you want them to be no matter what. So both of these points and matrices will place a part coordinate system in relation to an assembly coordinate system. So for example, if we look at this tank right here, you can see my hatch, my origin of my coordinate system is right here. And in my tank, my coordinate system origin is right here. So if I just placed that origin and grounded it, it would basically put this hatch right here in the middle of my tank, obviously where I don't want it. That's not going to help me get inside. But that's where it would put it because it's mating up my coordinate system with my part with my coordinate system of my tank. Now, as I mentioned, we can use either points or matrices, and it's important to understand the difference between the two and when you need one versus the other. So putting in the hatches is a good example of when to use one or the other. In this case, notice that in the front, we want our hatch to open this way, which happens to be the way that it comes out of the box. And if you notice, my Y and my X axes are the same in my part as they are here inside of my tank. The back one, on the other hand, we want to rotate that around the Y axis 180 degrees. And so that one, my X axis is backwards or inverted from the X axis on the other one. And that will also invert my Z axis, even though you can't see that right here in this view. So in this case, because my coordinate system is the exact same orientation as my assembly, I only need a point to place this. Whereas here, I need a matrix because I'm going to need to rotate it and then put it somewhere where I need it to be. So that's the difference. In one, if you need to rotate it, you got to use a matrix. If it's the exact same orientation as the assembly that you need it in, then you can just use a point. So let's look at how matrices work. And by learning how matrices work, points are just a subset of a matrix, which I'll get to that in just a minute. So a matrix for Inventor has 4 rows and 4 columns. You can see there's just a bunch of numbers. The top 3 rows and columns here, this represents a unit vector for each major axis. So these first 3 numbers right here represent the unit vector for the x-axis, the y-axis, and the z-axis. Now, if we look at our coordinate system right here, if I were to draw a vector or a line from my point of origin out 1 unit in my x direction, which would be my x-axis, my point here would be 1, because I'm 1 in the x direction. Notice I didn't go up or down, so I'm 0y, and I didn't come out of the screen or go into the screen at all. So I'd be 0 in my z direction. Same thing on the y. If I drew a line going from my point, went up 1 unit here, then my point would be 0 in the x, 1 in the y, and 0 in the z. So you can see how those match up here. 1, 0, 0, this is my x-axis. 0, 1, 0 is my y-axis. And 0, 0, 1 will be my z-axis. Now this is what we call the identity matrix. And basically, if you bring in any part and you say place at origin and ground it, that's exactly what it's doing behind the scenes. It's placing it according to this identity matrix that you're seeing on the screen. Now these last 3 numbers right here represent the offsets. So this would be my x offset in my assembly. This would be my y offset in the assembly. And this would be my z offset in the assembly. And so this basically gives you a point. Instead of saying I want my point to be at the center of my part of my assembly, you're saying I want to offset my part somehow, which we'll get to an example of that in a minute. Now this last row is always 0, 0, 0, 1. I'm not sure exactly what it means, but you'll be fine. You always leave that 0, 0, 0, 1. So you never are going to have to worry about these last 4 numbers. It's these first 12 numbers that you're going to need to learn to understand how they work, so that if you want to bring parts in using matrices, you can orient them and put them exactly where you want them to be. Now, as I mentioned, for the hatch in the rear of the tank, we actually need to rotate it 180 degrees. So instead of using the identity matrix, we're going to need a different matrix. So what works easiest for me is I say, okay, what is my x-axis from my tank? So you can see right here, if I look at my x-axis and I draw the line from here to here, and by the way, what I did with my part here is I oriented it exactly the way that I wanted it placed inside of my assembly. So remember, we want it rotated 180 degrees in the back. So this shows how that would fit in. So notice that in this case, my x would be -1, right? Because we're now on the negative side of x. So it'd be -1, 0, 0. My y is the same in both, so that would just be the same 0, 1, 0. And then as we rotate that 180 degrees, we're actually changing our z-axis from being in the positive z direction to the negative z direction. And this would be the positive z direction. This will be the negative z direction. So that becomes my matrix to flip it over 180 degrees. Now, in addition to that, we also want to locate it in the right spot. Because like I mentioned, even if we rotated it 180 degrees, if we just lined up the 2 origin points, the hatch would be here in the middle of the tank, which would really help us very much. So you can see by looking at this, let's look at the x value first. Because of where they put the origin inside of this hatch, it'd been a lot easier if the origin were in the middle rather than off to the side. But because they put it on the side, we're actually going to need to move it over in our negative x direction, because remember, we're in the context of the assembly. So I'm going to need to move it over, in this case, it's going to be 10.625 inches, so that the center of my hatch will line up with the center of my tank. Then what I'm going to want to do is I'm going to want to raise this up so that it's on top of my tank. You can see that from the middle here, that's our radius. Our radius is the OD of the tank divided by 2, right? Because the radius is diameter, half of your diameter. Again, notice that where this is, that would still leave a good portion of our hatch buried inside of our tank, and we don't want it buried in the tank. So we just have to also offset it another 3 inches to get it high enough so that we're not interfering with our tank. Now all of that, you can see here's our origin from the top view. So that would move it over this way and it would lift it up to the top, but we would still be in, near the center of our tank, not out here where we need to be. So the last part is in the Z direction. And remember I said this is the negative Z direction. So the length of our tank divided by 2 will bring us half the distance to the tank, which will put us right here at the end of the parts of our tank that have the shell plates, not including the dish head. Then you could see that we want to give the user the option to decide how far from this edge they want to place it. I called that parameter our rear hatch offset. So we would come back that far. But again, notice that my point of origin is here. So when we go tank over 2, my hatch is hanging off the end here. So not only do I have to go the distance of that offset, but I also need to go the full distance of my entire hatch so I get this placed where I want. So I need to add another 21.5 inches. So this formula right here, regardless of how long our tank is, regardless of whatever offset value that the user selects on where exactly they want to place that hatch, it's always going to come in at the right location where we want it to be. And this is, so if I only had to have a point, this would basically be my point. But again, because we needed to rotate that 180 degrees, then I need an entire matrix. And so you can see here is my rotation matrix. Right here is the actual offset values that I need. And the way that we write that in code is we create this matrix, and notice -1, 0, 0, minus 10.625, 0, 1, 0, and you can see the rest of it all right here. Now in Visual Basic, I could write this as one line with 16 values spread out in a single line, and I actually do that a lot just because I'm the kind that likes to save space. But it is easier to read if you hit enter after each 4 spots, and you can tab, you can space, you can do whatever you want to get these to line up. Visual Basic will let you spread a command out over multiple lines when you're doing this. So if it's easier for you to read, go ahead and feel free to do this. But again, I just wanted to help you understand how matrix math works. Once you learn how to do it, it's extremely useful to do this. And like I said, it's a nice, quick way to guarantee that the parts are going to come into your assembly exactly where you want them to be. Now, the next topic I wanted to review is passing parameters between files. So the way that I set up this data set is at my top level, I pretty much have all of the different parameters that I need. And when the form comes up and the user's changing all of these different values and options, it's actually changing those parameters in my top level part. Now, as soon as someone says build a tank, it's going to bring up my template first to build the tank body. Well, the tank body needs to know what those options were I selected in my top level. So what I do is I pass those parameter values down to my tank body assembly, and then I tell it to go build itself. And it builds itself, and then once it builds itself, then I bring it into my assembly and I place it exactly where I want it to be. And so what I do is I have a lot of the same parameters in my tank body, in my gun line assembly template, in my skid assembly template. I have all of the parameters that I need in each of those, and I pass it from high level assembly down to sub-assemblies and even down to the constituent parts so that they know how to update properly and I get everything looking exactly the way that I need it. So like I mentioned, the best practice is to have these parameters in all these different files. I name them the same. When you name them the same, it makes it really easy to go through each assembly and to understand how your parameters are being pushed from one file to another. Now, I do want to point out that iLogic makes it really easy to pass parameters from an assembly down to its child components. And it uses the component instance name. So it's important to know that you don't reference the file directly. You just reference this component instance name. And this component instance name, you have complete control over it. It does not have to be the same name as the file. And I use that pretty liberally so that I can get this name to be exactly what I want it to be. I just point that out because you'll see that throughout. You'll see me changing the instance name inside of assemblies. It just makes it easier so that when I pass parameters, I know exactly what this is going to be named no matter what size they select. Now the last three parts that I just talked about, this is a process that's used over and over and over again in this template that we're providing to you. We first create new copies of files that are needed. Then we make sure that our assemblies that have been copied are referencing the right new copies of the individual component files that we copied. Then we place the component in the top level assembly. So now we've created new copies, we've set it up properly. Now we bring it into our top level assembly. And then finally we pass the parameters to it so that it can update itself and it can be the right size that we need. And you'll see that when we actually get into the demonstration part of our presentation. Now, the last important topic I wanted to cover that will help you understand how the code is laid out and how it works is what I did. For example, if we look at our skid assembly, actually we'll look here at the gun line assembly since that's what I have here. So I first started by building my gun line sub-assembly. I thought, what are all the parameters that are important to me? I need to know where these holes are. I need to know how many downpipe nozzles that we have that are going to spray their media into the tank. I obviously need to have some end connections here. And what I did is I built that in isolation. All of the rules to create a gun line are contained within this gun line assembly. Then once I get everything working, I'm like, fantastic, I got this working and creating the gun line exactly the way I need it to. Then I bring it into my top level assembly and I build my top level assembly code that basically creates my new gun line assembly and passes the parameters, and I let the sub-assembly do all of the work itself. This makes code easier to troubleshoot when there are problems because if my gun line assembly isn't updating right, I know I need to go to my gun line sub-assembly, find out what's going wrong, and fix it. It also makes it easier when you're building automation to start at the smallest level, get that automated first, then go up a level, get that automated and get that working with the automation that you already created, and keep going up until you get to the very top level. And now you have this nice hierarchical structure where all of your sub-assemblies, all of your parts know exactly how to work together to get the final configuration that you're looking for. Now, a couple of good examples of when you're going through the code that we've given you here as part of the starter kit. A couple of good examples to go to is the tank body subassembly. You'll see a lot of code of how it puts itself together and builds itself. And another one is the gun line subassembly, the one that you see right here. This has quite a bit of code in there that shows how it's building itself. And we're just calling it from the top level assembly. So it makes it a whole lot easier to build code and to make everything work the way that you want it to. Now, the final thing I wanted to cover before we go into the quick demonstration here is the user interface. So in the user interface, we have a project ID, and the project ID is very important because you can't duplicate using project IDs. I basically use this value, and it could be anything you want, by the way, it's just text. But it will basically create a new folder in your workspace with the project ID, and all of the project-related files that are unique for that configuration will be copied into that folder and will also be given a name with the project ID appended at the end. That way, all of my files that I create for each unique configuration, I make sure that I don't have duplicate file names, and I make sure that everything has its own nice, unique name. Now here we have the tank OD. Notice we have this nice little slider control so that you can quickly move it back and forth and pick the OD of the tank that you want. The valid ranges are from 24 inches to 144 inches, and we allow them to vary that in 6-inch increments. Then we have the length of the tank, and the valid ranges here are 36 to 600 inches. And again, that's all in 6-inch increments, and you can move this back and forth, and it will always make sure that your value is a multiple of 6. Then we get to the inlet information, and for the inlet, I give a few options for sizes. You can have 3-inch, 4-inch, 6-inch, or 8-inch. You can pick, do I want it on the front? And if you want it on the front, it will be at the top of the dish head plate. Or you can put it on the top, where it will go anywhere along the top in the center of the tank. You can also determine the offset. So if you put it on top, it'll be the offset from the front of the tank moving backwards. If you're in the front, it'll be the offset from the top of the tank coming down. And then you'll see this everywhere in the interface. Anywhere where there's a connection to the outside of the tank, you could pick a flange type. And the 3 types of flanges that I'm supporting, or we're supporting with this application, are lapped, slip-on welding, or welding neck. And then you can also pick the end connection. So you can have it open, you can have it capped, or you can have us put a valve there on the end. Now moving to the next page, or the next tab with the drain info. So technically you can pick, do I want a front drain, do I want a back drain? So you can have no drains, you can have one, you can have both. They're completely configurable. And again, just like with the inlet, you can choose the flange type and how you want your end connection to be capped. Moving over to the tank access, here's where we start to have some preconditions. So a manway, just because all the manways we're using are pretty large, we can only put manways on tanks that are 48 inches in diameter or larger. So if we go below 48 inches, it's actually going to automatically uncheck this box, and it's going to gray out all of these controls so that we can't put a manway on there. If assuming that you are 48 inches or higher, you have the option to include one or not, and there are 3 different sizes: 21 inch, 22 inch, and 25 inch. These are always placed on the rear dish of the tank, so you can't choose I just have predefined rules. Again, though, if you want to make it configurable where to put it, have fun with this data set. It doesn't even have to make sense. Just it's fun to go in and to try to figure out how you get it to do whatever you want it to do. Then we have the ability to add hatches. And again, hatches are only valid for tanks with an OD of 60 inches or larger. They're always placed on the top, either in the front or the back. Again, you have the option to include it or not include it. And we only have one size, so there are no size options, but we do let you pick how far you want it to be offset. For the front hatch, that would be the offset from the front edge. For the rear hatch, that would be offset from that rear edge of the tank body. Then again, for tanks that are 60 inches or larger, you can put a gun line in. Again, the option to include it or not. The only 2 sizes we support for gun lines are 4-inch or 6-inch. Again, just like some of the others you've seen in the past, for the flange options, you can pick the flange type and the flange cap or the flange end connection. Then finally, we get into the sump info tab. Again, only available for tanks that are 60 inches or larger in the outer diameter. Option to include it or not. The only 2 available sizes are 6-inch or 8-inch. You can set how high you want that to come, and that's measured from the bottom of the tank, not the floor. You can also choose how far you want it to project out from the front of the tank. And then again, just like the others, you can choose the flange height options. What type of flange you want and how you want that to be capped. So let's go ahead now and let's open up our Create New Tank. And again, just like I mentioned before, when you open it up, it's going to open up to a blank assembly. And it's going to go ahead and it's going to load up this form. Now, before we get started filling this out, I just want to make sure that you know, here's where you go for parameters if you need to change the project path, the library path, or the template path. Here you can see all of our user parameters that were created to make this automation work properly. And if you need to access the iLogic code, here in iLogic, you go to the tab, and here's where you can access the rules. You can right-click it, say Edit Rule. That will take you in here. Now, one thing I want to point out, I did create different subroutines and functions for all of the different code that puts together the tank. So if you want, you can right-click here in the interface. You can go to Collapse Definitions, and if you want to go see how we created and configured the skid, then you can just expand that, and you can go in and see all of the code that we used to create and configure the skid. So it makes it easy to go in and find what you're looking for and see the code based on what you're interested in looking at. Now, these are the snippets that come out of the box with Inventor. Again, if you load that custom snippets file that I included in part of the documentation folder, then it will put in all of these different snippets that you can just literally right click, and it will bring all of those into your window here. The final thing I want to cover before we do the demonstration is if I do my forms, this is where you can edit the form. And there's actually quite a bit that you can do with iLogic. There are some limitations. Autodesk wanted to make it easy to create the forms with just drag and drop techniques. So you can see I gave some pretty good examples of how to go in and create the form. You might want to look up in the Inventor help file to get a start of understanding how you put these together. But again, there's a pretty good example in here that shows you how the form is put together and how all of this works. So let's go ahead and launch our form. We're going to start with a project starter kit 1234. Nice original name. Now I want you guys to notice here, let's pretend we have some front and rear hatches. As I come down and I get to 60 inches, notice that it's still going to let us put front and rear hatches. But as I go below 60 inches, it's now going to clear the check boxes and it's going to deactivate these controls. So I can't select it. And I like to do that to make sure that people can't make improper choices here inside of these forms. Then if I keep going down below 48, then the same thing happens for my manway. So that's just a nice little touch that you can do to your forms in iLogic to make it so that you're controlling the choices someone makes to try to minimize the chances of them picking some invalid combinations of choices that don't really work. So we'll go ahead and we'll put our inlet on the top. I'm going to go ahead and just pick 80 inches that we're going to offset it, and we'll just pick a random length here. We'll go ahead and put some drains. We'll keep valve and capped. That looks perfect. Then for our tank axis, we'll do a 25-inch manway. We will put both a front and a rear hatch, and maybe we'll offset our front one by 4 inches and our back one by 12 inches so you can see the range of difference there. We'll go ahead and we'll include the 6-inch gun line, and again we'll do a valve, and actually let's make the front a valve and the back one we'll just cap that. And then finally for the sump, we'll make that our 8-inch version. We'll have a 15-inch projection. We'll leave the height at 20 inches and leave that the way it is. So now that I've made my options and my selections, I can click Create New Tank. And what it's essentially doing now is my code is going through grabbing files from the template library that I built, copying them over to a new folder structure that I built for SK1234, and it's passing parameters to each of these sub-assemblies. The sub-assemblies are passing those same parameters down to their respective parts. And by doing that, you can see all of these pieces starting to resize automatically and to build themselves according to the configurations and the options that I selected. Now, there are a few bugs in here. I wish I had had more time to go and make this work perfectly, but due to some time constraints, I had to rush some aspects of this a little bit more than I wanted to. That's okay though. If you come up with some inlets that are sticking out of the tank a little bit, feel free to figure out how do I fix that. and make it so that it comes out accurately. That's part of this whole process, is for you to have a data set that you can get in and play around with. So here I'm going to just turn off my work features so that we can see the tank. Notice that if we look at the bottom side of the tank, all of our saddle supports fit in exactly where the seams were. So I added some code to make sure that these saddles fit exactly where they're supposed to based on these seams. You'll notice we have the drain in the front and the sump that are both capped, which is exactly what we asked it to do. We have this gun line assembly that has a tank in the front. If I look at this, I'll notice that all of my downpipes with my nozzles have been appropriately sized, and the length is just right so that it'll blow our media down to the bottom of the tank exactly where we want it. You can also, if we look at our sump assembly, you can see we built it so that it has a bracket right here that rests on the bottom of our tank at the center line of the tank. And we have our pipe offset, and it knows exactly how long it needs to be so that our pipe comes out with the 20 inches height from the bottom. And we took it 15 inches from here all the way out. So you can see how we can go ahead and we can build our logic so that we allow the users to configure a tank exactly the way they need. Last I want to point out, notice that we have a 12-inch offset on the rear, but if I go to my front, we only have a 4-inch offset. So again, all of this code is in there. As I mentioned, all you have to do is go to the rules, right-click, create new tank, and this will walk you through all of the logic. I hope you guys have fun with this. I hope that you guys enjoy playing with it. Again, I've said this a few times, and I want to say it again. I encourage you guys to go in and play around. It's okay if, Inventor comes up with some error messages saying that you did things wrong. That's how we learn how to get better at programming, and that's how we learn how to get our applications that much more robust. So thank you for joining me today. I hope you enjoy the kit. If you have any questions, by all means, please reach out to us here at KETIV. We are here to help you. After you do this, if you decide you want a much bigger application and you need help, we do provide these services as well, where we can come in and we can help you architect the solutions. We have a whole team that helps build these types of solutions. And so we can also help take you guys to that next level where you get your designs automated and you can get your product designed that much faster and get your product out to your customer as fast as you possibly can. Thanks again, and I hope that you all have a wonderful time.